This is the screencast for section 2.2, example 6. We're going to model free fall speed versus distance. So in other words, an object, no matter how far, if you drop it from a certain height, the farther it falls, the faster it goes. But that's not a linear relationship. It's not like for every 5 feet it falls, it gains 3 miles an hour. It is a power regression relationship, and we'll see that after we calculate the statistics and find our regression model. So use the data in table 2.11 to obtain a power function model for speed p versus distance traveled d. Then use the model to predict the speed of the ball at an impact given that the impact occurs when d is about 1.8 meters. So my distance is going to be in L1, those are my x values, and my speed is going to be in L2. So in other words, this function is p of d. My speed, the speed of the object depends on the distance it has fallen. Now, if we remember back in the definition of a power function, k and a are non-zero constants. So we run into an issue in our data here. In L1 and L2, we cannot use the origin 0, 0. So I'm going to leave out that data point in my lists. So I'm starting off with the second data point. Now I'll be able to calculate a power regression, put that into y1. So my function of speed my function speed depending on distance, so as a function of distance, is 4.03 x to the, looks to be about 0.49. It says then use the model to predict the speed of the ball at impact, given the impact occurs when d is about 1.8 meters. So I'm going to zoom 9. That fits pretty well. But I need to change my x max to to about 2, which means I'm going to change my y max to maybe 8 as a guess. Now I can see the y values all the way out to the end of the x values I want to see, and I can plug in 1.8 into y1. So the speed of the ball is about 5.39 meters per second at time of impact. Number 57, Velma and Reggie gathered the data in table 2.13 using a 100-watt light bulb and a calculator-based laboratory, or CBL, with the light intensity probe. So first we want to draw a scatter plot of the data in table 2.13. Now I've put this data into L3 and L4, so the distance is going to be L3 and the intensity is going to be L4 because the intensity of the light depends on the distance from the intensity probe. So to draw a scatter plot, I changed my x list to L3, my y list to L4, and now I'm going to hit zoom 9. So there's my scatter plot. Find the power regression model. Let's go with stat calc alpha A. Again, my x list was in L3. My y list was in L4. I'm going to store this into y2. So there's the power regression value. Is the power close to the theoretical value of a equals -2? Yeah, the exponent that we got is -1.99, which is very close. So yes, it is close to A equals -2, the theoretical value for the intensity of the light depending on distance. Now it says superimpose the regression curve on the scatter plot. So we'll hit graph. And that does match as well as it says it would. It was a negative correlation, negative power regression correlation, very close to -1. So that is a very good lineup between the regression I found and the data points. Now it says use the regression model to predict the light intensity at distance of 1.7 meters and 3.4 meters. So I need to make my x values go all the way out to 3.4. So I'm going to go farther than that. I'm going to change my x max to, let's go to 5. So I'm going to hit trace, go to y2, the function that I'm using here, and I'm going to put in 1.7 meters. Again, I could use the regression I came up with and then calculate, but the calculator has the ability to do this for me, and there's no restrictions against using my calculator in this problem, so I may as well use it. And then the other value I want to find is 3.4. So at 1.7 meters, the light has an intensity of 2.76 watts per meter squared. And then at 3.4 meters away, the light has an intensity of looks like 70 watts per meter squared. In other words, what that's measuring is watts per meter squared. Just means, watts are intensity of a light bulb, and they're looking at the intensity, how much light is hitting a square meter of material.